As we move into right triangle trigonometry, we have to say a few words about how we name the different sides of a triangle. So here we have a diagram. We have an angle theta that's labeled, and then we have names for the different sides. Now the hypotenuse will always be the hypotenuse. It's always the longest side, and it's always across from the right angle. But the other two sides, these are just typically known as legs, and we have to be able to identify one from the other. So relative to the angle theta, we have an adjacent side. It's adjacent to the angle. And then we have the opposite side, which is opposite the angle. So when we see the words adjacent, opposite, and hypotenuse, they always refer to parts of a right triangle relative to some labeled angle. Now when it's labeled this way, oriented this way, this is something that students are pretty familiar with. But as soon as you get a different orientation, students can sometimes struggle with how they want to view these things. So let's call this angle here alpha. There's your right angle. Where's the hypotenuse? Now some students will say hypotenuse and they'll look for this sort of lower left to upper right diagonal and label this the hypotenuse, and that's just not how it works. Hypotenuse is always relative to the right angle. It's the longest side and it's always across from the right angle. This side right here, that's the adjacent side because it's adjacent to the angle, which makes this one the opposite side. Now this isn't particularly confusing if you take your time. But if you go too quickly, you might make mistakes. And there's something else that happens, which is that these names are relative to the angle. So if we call this angle here beta, all of a sudden some of these names are going to change. The hypotenuse will still be the hypotenuse, but now this side over here is opposite. It's the opposite relative to the angle beta. And this is the adjacent side, and it's adjacent relative to beta. So always keep in mind that adjacent and opposite are relative to the angle that you have labeled, and there are problems where you're going to have to interact between two different labels, and that's just how it is. So pay attention and take your time with these things. Earlier, we had defined the trigonometric functions in terms of points on a plane. It turns out that there's a way to use right triangles to talk about these things, and this is known as right triangle trigonometry. So SOHCAHTOA. This is the term that most students remember. It's just a mnemonic device. It's just a bunch of syllables that kind of sound good together. And so SOHCAHTOA, this is how students remember this. What does it mean? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So that's the SOHCAHTOA. And all it says is that if we take these these parts of the right triangle relative to some angle, we can actually set up relationships that give us these different trigonometric functions. And we'll see later how these relate back to the formulas we used using points on a plane. So here's an example. Determine sine of alpha, cosine alpha, and tangent of alpha given this diagram. Now the first thing you'll notice is that the alpha is labeled here, but the hypotenuse is across the bottom. We don't know the length of the hypotenuse, so maybe that's the first thing we should start with, because we're going to need all three sides to calculate these values. So we can use the Pythagorean theorem. We'll just call this thing c. So c squared is equal to 4 squared plus 7 squared. 4 squared is 16. 7 squared is 49. 16 and 49 is 65. So c is the square root of 65. So we can label that. Excuse me. Now we need to do sine, cosine, and tangent of this angle here. SOHCAHTOA. Again, a bunch of meaningless symbols that remind us what the relationships are. So sine of alpha is the opposite over the hypotenuse. Now in this case, here's our angle alpha. The opposite side is 7. And the hypotenuse is the square root of 65. Right, so again, the hypotenuse is the longest side down here. Cosine of alpha is adjacent over hypotenuse. So the adjacent side, adjacent to the angle, is 4. And the hypotenuse is square root of 65. And lastly, tangent of alpha. Tangent, the TOA, is opposite over adjacent. So the opposite side is 7, and the adjacent side is 4. So using SOHCAHTOA to calculate sine, cosine, tangent of a particular angle in a right triangle, it just comes down to labeling it correctly and then not making mistakes when you set up these relationships. Now at this point we have two different presentations of the sine and cosine function. We have the sine and cosine functions in terms of points on the plane, and we have the sine and cosine functions in terms of these right triangle relationships, and of course tangent comes along through the relationships that we've set up. And so the question is, how do these things all match up? So let's start by drawing a picture that corresponds to this, the points on the plane. So we have a point xy in the plane. The distance r is the distance from the origin to that point, and that creates an angle theta. Now, in order for us to make this picture look like this picture, what we have to do is we have to create a right triangle by simply dropping that point down to here to create that triangle. Because now if we think about it, x corresponds to the horizontal distance to the point, and y corresponds to the vertical distance to the point. And we can see that we have a right triangle labeled. Y over r. Y over r. Well, this is the opposite side, and that's the hypotenuse. Sine is y over r. Sine is opposite over hypotenuse. And you can work your way through. Cosine is x over r. X, well, that's the adjacent side. R is still the hypotenuse. So cosine theta is adjacent over hypotenuse, which is what we have here. Tangent theta is y over x. Here's y. Here's x. Opposite over adjacent. Tangent theta is opposite over adjacent. And so this shows us how the two pieces actually fit together into one. It's just a matter of creating a right triangle picture out of our points. You could have also done this the other way around. You could have started with a right triangle and then simply embed it into the plane. And as long as you set it up with the angle in the appropriate place, you will get the same relationships out of this. Now there is one thing to say about this, which is that this relationship right here, this only works within the triangle, which means that this only works for acute angles. These definitions work all over the plane. And so there is a little bit of difference, but this just shows that they represent the same concepts.